In question 1a, we created a discrete time cosine signal in Matlab with time index from 0 to 60 and plotted it using a stem plot. The signal is defined by amplitude, angular frequency, and phase offset. For 1b, the signal length is calculated as 61 samples since it goes from 0 to 60 inclusive. In 1c, we check if the signal is periodic because the fundamental period is approximately 6.67. In question 1d, the code was modified to generate a second discrete time cosine signal x to n with different parameters: amplitude 3.5, frequency 0.44 pi, and phase offset of negative pi over 3. The two signals are plotted side by side for comparison. For 1e, we analyze whether x to n is periodic since its frequency is 0.44 pi, which corresponds to a fundamental period of approximately 4.4505. Finally, in 1f, we compare xyn and x to n. Xyn has a lower frequency, smaller amplitude, and phase offset pi over 4, producing smoother oscillation, while x to n has a higher frequency, larger amplitude, and phase offset of negative pi over 3, resulting in faster oscillation. Both signals are non-periodic. In question 2, we analyze a complex exponential signal defined as xt equal to 2 e power of negative alpha t e power of j omega t, with alpha equal to 0.4, omega equal to 3.5, and t ranging from negative 3 to 5 in step of 0.01. The Matlab code compute the real and imaginary part of xt, then plot them together in the first figure. The real part shows the cosine-like oscillation modulates by exponential decay, while the imaginary part shows the sine-like oscillation with the same decay. In the second figure, the code plot the magnitude and phase of the signal. The magnitude exponentially decay over time due to the damping factor alpha, and the phase increase linearly due to the angular frequency omega. We also create a similar code for the signal xt equal to 5 e power of negative 0.3 t e power of j6 over the interval 0.6.
For question 3, a MATLAB code to generate and plot H1n, X2n, and Xn. We generated three signals H1n, H2n, and Xn of the range -6 to n to 6. H1n is a combination of the impulse at the 0, 2, and 4 showing this discrete spike. H2n is exponentially weak sequence limited between n equal -2 and n equal to 2 showing a decaying pattern. Sn is another exponential.
For the question 3b, system H1 followed by the H2, we combo the Xn with H1n to get intermediate output Vn, and then combo Vn with H2n to get the final output of Yn. The intermediate output Vn display a wider range and combination of the input exponential shape modified by H1. For the question 3c, for the H2 followed by H1, the reverse order. We reverse the order by combing Xn with H2n first, then with H1n. The new intermediate Vn show a different shape compared to part B, reflecting the different first system effect. The final output Yn match exactly the result from the part B, confirming the commutative property of the convolution. For the question 4a, the method goes to the combo of the xt equal to trie t minus 2 over 3 and ht equal to e power of negative t sine t times with the ut. That in the manner we define the st as a triangular pulsate at t equal to 2 with a weight of 6 and ht as an exponentially decaying the sinusoid starting at a t equal to 0. We plotted both signals and computed the convolution numerically using the convolution function, displaying all three plots in a single figure with a subplot for the clear comparisons. The convolution integral involved integrating the product of the x tau ht minus tau over the interval where the both signals overlap, because the xt is finite in duration and ht is causal. The integration limits depends on t, although this integral is complex due to the combination of the exponential decay, sign, and the triangular shape. It describes how the output signal is a weighted sum of the shifted input.
Hi and Assalamualaikum. Question 5a. An ideal linear phase low pass filter has the following frequency respond to function. After I've solved the question, I got the 4 per pi since times 2 bracket t minus 3 per pi. Then I compute and plot the impulse response of the filter. The impulse response show that filter introduced a 3-unit delay typical of a linear phase system that preserve waveform shape but shift in the time. For question 5b, input signal be xt equal to sinus of 4t and the output response yt equal to ht times xt. Then I plot both xt and yt on the same figure using subplot. This is how I solve. For xt, we should contain high frequency component that low pass filter remove much of the signal's energy, resulting in smoother and Question 5c, input xt be a periodic square wave with a period t equal 4 and amplitude a equal 1 divided over t equal to negative 10 to 10 and equal to 20 harmonic to construct the signal. After I plot xt and yt, I got the two different graphs, which is square wave and rounded waveform. When a square wave reach in high frequency, its filter is sharp, it just as smooth out, producing a rounded waveform. Only the low frequency Fourier component remain. In conclusion, the ideal low pass filter delay signal and remove high frequency content.
After I ran the codes, refer to the transfer function from the question. With the region covariance defined RES bigger than 2. To analyze the system, we input the transfer function into Matlab and generate the pole zero plot. This plot visually shows the location of pole zeros on the complex plane, which is crucial for understanding the system stability and frequency response characteristic. In this question, we focus on calculating the impulse response of the system from given transfer function using residue method. The transfer function will decompose in polar partial fractions mentioned. This allows us to directly apply inverse Laplace transform. This shows stability is not only about growth, it depends on the region convergence ROC. Since the ROC is given that RE bracket S bigger than 2, all poles are excluded from the region and the system mathematically considered stable with ROC. For question 6c, this transfer function was implemented in Matlab and we plotted the system's response and given input. Depending on the xt is whether it's in step, exponential or another function. The output yt show the system natural behavior such as damping, oscillation or steady state. From the graph, we could observe whether the response over them